Thank you very much for this introduction. My tutorial will be based on old results, so mainly on papers by Itchin, Donaldson, and Kronheimer. You can also find some of the things that I will talk about in one of my papers, hyperkaehler structure and infinite dimensional Grassmannian, where we got a structure on the infinite dimensional space related to the Grassmannians using a hyperkaehler quotient in infinite dimensions. There are finite dimensional papers also. I didn't put every reference, but perhaps this one, hyperkaehler structure on cotangent bundle of Hermitian symmetric spaces. We will not go into very deep theory. My aim today is to introduce what a Kähler and hyperkaehler structure is, adapted also in the infinite dimensional context. I will briefly talk about Nahm's equation. I will not go into depth here because my time is limited, but I will give some ideas that is relevant here. So what is a weak Kähler manifold? A weak Kähler manifold is a Banach manifold in the Banach context, but you can make sense of this in the Frechet context or even beyond. So the definition is the following. You have a Banach manifold with a weak symplectic form, and now I think everybody knows what weak means. It means in particular that you have just an injection from the tangent bundle of M into the cotangent bundle using this symplectic form. And there is also a weak Riemannian metric, and weak means exactly the same. You just have an injection from the tangent bundle into the cotangent bundle through the metric. And there is a compatibility condition between the symplectic form and the Riemannian structure. And it can be stated like this. If you look at the operator that you get when you try to write the symplectic form using the Riemannian metric. So recall that point-wise, here you have a pairing, which is symmetric. Here it's antisymmetric. And this operator I, in this case, should satisfy I squared equals to -1, meaning that it's an almost complex structure. But more should be true. The Nijenhuis tensor of this operator I should vanish. I recall what the Nijenhuis torsion is. This is this bracket here. This means that you have a formally integrable complex structure. In infinite dimensions, this doesn't lead to holomorphic charts, not necessarily. There are examples where you don't get holomorphic charts. But the idea behind is you are in a context where you have a Riemannian metric, a symplectic form, and a complex structure compatible. The idea. In this context, we can perform a symplectic quotient and Kähler quotient. And this is the next slide. So this is a finite dimensional version of a Kähler quotient. You start with a manifold, which is weakly Kähler, so in this finite dimensional context. So you have a Riemannian metric and a symplectic form compatible. And you suppose that you have a Hamiltonian action by a Lie group G, meaning that you have a moment map. We have seen moment maps yesterday already. And this action should preserve the Kähler structure. It should preserve the Riemannian metric and the symplectic form. Okay. Yeah. The group is real. It's a real group. Yeah. And then take a regular value of so in the dual space of the Lie algebra of G, which is invariant by the action of the group. Try not to. And you suppose that G acts properly and freely on the level set of this moment map corresponding to the covector that you have chosen. Then there is a Kähler structure induced from the Kähler structure of M on the quotient of the level set of the moment map by the group action. Let's go now to the infinite dimensional version of the theorem. Here you only have a weak Kähler-Banach manifold. The Hamiltonian action is by a Banach-Lie group with a moment map, so with value in the dual space of the Lie algebra. And again, you need some regularity condition on the covector that you take. You have a condition on the group, on the action of the group. This action should be proper and free on the level set. And then you add a condition which is really related to the fact that the symplectic orthogonal to the symplectic orthogonal of some space may not be the same. Here, in this context, you ask for decomposition of the tangent space of the level set to the moment map into two pieces. One is the tangent to the orbit of the group, and here you have the orthogonal with respect to the Riemannian metric. And recall that the Riemannian metric is only weak, so this is not automatic. This kind of decomposition is absolutely not automatic. But if you have this, and you are in this context where the group action is nice, then you induce a weakly formally integrable Kähler structure on the quotient space. So that was for Kähler quotients. Let me stress here that we don't need any Darboux theorem for make this work. And the price to pay is that the structure that we get downstairs may not be easy to be understood or written in coordinates. So that's one thing. But on the other hand, so it's a bit like a divorce between physicists and mathematicians. Physicists, they like to write in coordinates, and if they don't have Darboux, they may be not happy. Mathematicians, they are happy when something exists. So, yeah, we will see after that this kind of procedure allows to define hyperkaehler structure on manifold that we understand, but we don't understand really the symplectic forms and the structure. So it's a bit a mystery what you get at the end. Let me continue. We go to the hyperkaehler case now. So let me give a definition. A weak hyperkaehler manifold, in by contrast, it's a Banach manifold endowed with a weak Riemannian metric G, one Riemannian metric, and three symplectic forms. The symplectic forms are weak, and there are three of them, omega 1, omega 2, omega 3, and each of these symplectic forms is scalar with respect to the same Riemannian metric. One Riemannian metric, three symplectic forms, each of these symplectic forms is scalar with respect to Riemannian metric. This means that, in particular, you have three different complex structures, formally integrable complex structure, that you get by pairing, by expressing the symplectic form using the Riemannian metric. So you have now three complex structures. So here again is an Eisenhower torsion that you can use to check that the complex structures are formally integrable. And in this case, so the finite dimensional version of a hyperkaehler quotient that I'm given is in the paper by Itchin and collaborators. So it goes back to 1987. And it's the following. You have a hyperkaehler manifold and an Hamiltonian action of the group G for each of these symplectic forms. So you have actually three different Hamiltonians. that you put together in a function that goes from the manifold into the dual space of the Lie algebra of the group times itself times itself. So G star plus G star plus G star. And the group is preserving, sorry, this is a typo, or preserving all the Kähler structure, preserving this hyperkaehler structure. Again, if you have some regularity assumption for the value of the covector that you take, so now it's there are three elements of the dual space of the Lie algebra to be taken. And if the group acts nicely, then you get a hyperkaehler structure on the quotient, which is a level set of this moment map by the group G. So here the dimension is the dimension of M minus 4 times the dimension of the group. Now the infinite dimensional version of this in a weak hyperkaehler Banach manifold, endowed with a group action by the Banach Lie group. Again, we have some regularity assumption on the value that we get, that we take in G star plus G star plus G star. This should be a regular value. And the group should act properly and freely on the level set of this moment map. This is to ensure that the quotient will have a manifold structure. And we ask also for decomposition like this, where here you have the tangent space of the manifold that you started with. And here you have the tangent space to the orbit of the group. Here it's again a real group. So here is the tangent space to the orbit of the group, plus I times this tangent space, but for all of these three different complex structures. And then you have here an orthogonal to all of these, which will be the model space for the tangent space of the quotient. What you get downstairs is, again, a weakly formally integrable hyperkaehler structure. So let me give an example of this construction in this infinite dimensional setting. You start with a decomposition of your preferred Hilbert space, let's say separable, infinite dimensional, into two different pieces, H plus and H minus. Both are closed and let's say infinite dimensional. You can do it also for finite dimensional subspaces. And you look at it's an affine space. It's an affine space, so there is a translation by K times the identity on the first space. And then you ask that the projection, orthogonal projection on H plus of the element that you take, this is a bounded map from H plus to H. So this first projection should be L1, so it differs from K times identity by a trace class operator. And the second one is L2. And the group here is a group of unitary operators which differs from the identity by a trace class operator. So these are Banach spaces. Here's a Banach Lie group, and this is an affine Banach space. This Banach Lie group acts naturally on this affine space, and there is an Hamiltonian moment. There is a moment map. The action is Hamiltonian, and here you can write explicitly what the Hamiltonian is, what the moment man is. Sorry. So here we are acting on the tangent space of Nk, which is pairs of x like this, and the tangent space is where you forget about this translation. So small x is in Nk, and x is a bounded operator from H plus to H, such that the projection on H plus is L1, and the projection on H minus is L2. So here you see the moment map. And if we take the level set corresponding to this particular element, which is for the first entry, which is here in the dual space of the Lie algebra, so it's a trace of something, we take simply a coefficient times a trace, and in the two other entries, we take just 0. The level set of this map, modulo the action of G, is a smooth hyperkaehler quotient.
Yes.
Yes, so this is parameterized by K, indeed. We have a family, one parameter family of quotients.
You had MK.
Yes, and MK is also parameterized by K because here there is a K appearing here. You can put K equal to 1 if you want, but there is a one parameter family.
No, there is one quotient in each manifold.
For each K, you perform the hyperkaehler quotient. And then you get a hyperkaehler manifold.
Yeah, but from a different manifold each time.
Yes. Yes. But this K is just a parameter in the theory. It's relevant because at the end, what you get here is that this quotient can be identified with very natural manifold that we know in very different ways. So the first the first identification that you get is that this quotient space is diffeomorphic to the cotangent space of the connected component of the restricted Grassmannian containing H+. This is one thing. So we have seen the restricted Grassmannian in some other talks, so I will not define it properly, but let's say these are subspaces of your Hilbert space, which differ from the H+ that you were taking by a Hilbert-Schmidt operator. Hilbert-Schmidt deformation of H+. And this cotangent space, this is actually a Hilbert manifold, but here we performed hyperkaehler quotient in the Banach context with trace class operator and so on. And this was needed to make sense of the pairings and so on. The first identification, this quotient space is diffeomorphic to the cotangent bundle of the restricted Grassmannian. Second identification, the same quotient space is diffeomorphic to complex extension or complex orbit of the restricted Grassmannian. So how is it, this identification? Simply, an element of the Grassmannian is a subspace, a closed subspace in your Hilbert space. You can consider its orthogonal, which is another one. And its orthogonal will live in a kind of dual Grassmannian. Simply, if you exchange H+ and H-, if you exchange the roles, you will get another type of Grassmannian. And the complexified orbits are those pairs of subspaces which are in a direct sum like this. So here it's a Banach sum, so there's no orthogonality here. That means simply that these two spaces are complements of each other. And if you want to see it as a homogeneous space, it's simply the group GL2, so the group of linear invertible operators on H, which differs from the identity by Hilbert-Schmidt, modeled out by the diagonal group that you get, so GL2 of H+ times GL2 of H-. So if you compare it with the restricted Grassmannian, for the restricted Grassmannian, we have U here, U plus H+ and U H-. So if we look at what we got here, we have one Kähler quotient by So there's this quotient that we get by hyperkaehler reduction, and two different identification. One is a cotangent bundle, and the other one is a complexified orbit. All these maps here are commuting, and another way to see it is also using Stadl manifold, but I will not go into this. All this quotient can also be realized as a symplectic quotient in the complex category with an action of a complex group that you obtain from G by taking the polar decomposition. So the polar decomposition of this one will get it's a G times exponential of E, the Lie algebra of G. Yeah. Go on. So now I would like to, I have 5 minutes. I would like to introduce the Nahm equation and why they were studied, actually. So the first thing that I want to stress is that if you start with a compact Lie group, then you can write easily the cotangent bundle because there is a trivialization, or it should be a G star here in the, let's say we are now in a finite dimensional case, compact Lie group. So you can identify G and G star using the Killing form. So the cotangent bundle can be trivialized, and on the other hand, you have polar decomposition, which allows you to identify the product of G with its Lie algebra with G star, simply using here the exponential map and the polar decomposition. What you get when you start with as group the circle S1, you get that the cotangent bundle of S1 is C star, and if you start with SU2, then you get that the cotangent bundle of SU2 is equal to SL2C. But more is true, and this is a result by Kronheimer, so the reference is in the list of references I gave at the beginning. It is called hyperkaehler structure on the cotangent bundle of a complex Lie group. So you start with a compact Lie group, and now you look at the cotangent bundle of the complexification of G, cotangent bundle of GC. So the cotangent bundle of this complex group carries a hyperkaehler structure, and this hyperkaehler structure is invariant with respect to left and right translation by element of the compact group G. And again, you have a trivialization. Oh, this is a typo, sorry. So yeah, this is a typo. We'll see, I probably have it after, yeah. So if you trivialize, this is not what you get. What you get is the group G times the Lie algebra times the Lie algebra times the Lie algebra. So 3 times the Lie algebra. So this is simply a copy and paste from the previous slide. Sorry, forget this slide. Yeah, there is really a problem with this. Did I get back? Yeah, okay, this slide just is not working properly. But let me state it. You have a compact Lie group, and the cotangent bundle corresponding to the complexification of this group carries a hyperkaehler structure. And if you do this with S1 as a group, then the cotangent bundle of the complexification is S1 times R to the power 3. So this theorem uses Nahm's equations. The Nahm's equations are the following system of equations for Lie algebra valued function of one variable. So AI are function from a real variable, actually from 0 to 1, with values in the Lie algebra, and you have these 3 different equations. We look at C1 solutions, and we denote the space of solution by n.
equations.
Sorry?
It seems that they are not symmetric, or
No, they are not. They are not.
the second equation
Yeah.
is different from first.
Yeah. And this is related to the following fact. Nahm's equation actually corresponds to the SU2 invariant self-dual connection on a trivial principal J bundle over R4 without 0. So you identify R4 with F3 times R. So there is one dimension that is special, and you perform the action of SU2 on R4. Simply SU2 acts naturally on F3. And this is what you get. These Nahm equations are actually self-dual connections, this trivial principal bundle. And you can recognize here gauge transformations. And again, it's not symmetric. Here is the relevant gauge transformation. Here is nothing.
It's derivative, maybe it's a radial coordinate or what is it?
Sorry?
I mean the coordinate with respect to should take derivative in the Nahm's equation.
Yeah, here. Because these functions are function of one variable. And my parameter is called S.
So I'm asking what is the physical interpretation of this parameter S?
This is the direction of time. This is time.
I think. Previous slide. There is no A4. The last equation.
Yeah, no, A4 A3 should be A.
I think it's A2, but I'm not sure.
0, 1, 2, 3. Let's see.
There are four functions and three equations.
It's 2, yeah, you're right.
I
Yeah,
think it's 2.
yeah, it's 2. Thanks. Yeah, it was a bit late yesterday when I did these slides after the reception, so I'm sorry for the typos. Okay, let's go on. So the theorem by Cronheimer is the following. If you consider the normal subgroup G0 consists of paths with prescribed value at 0 and 1, so starting from the identity, then you can perform the quotient of this of the space of solution of Nahm equation by this group, and this is a hyperkaehler manifold. And the hyperkaehler structure here comes from the fact that you start with something with four maps, A0 to A3. So you use the hyperkaehler structure, natural hyperkaehler structure of R4 in this context. And for one of these complex structures that you get on this hyperkaehler quotient, the underlying holomorphic symplectic manifold is T star GC, the cotangent bundle of the complex C-side group. A remark, and I will not go into this, if you replace the interval 0, 1 that we were using here by something which is not compact, so 0 plus infinity for instance, and if you had some boundary condition and a lot of analysis, you can use this procedure of infinite dimensional hyperkaehler quotient using Nahm equation to put a hyperkaehler structure on complex coadjoint orbits. And again, the price to pay is that these structures usually are not very explicit. We don't know them well, and this is probably very intriguing. Yes, I think that's more or less what I wanted to say. I should add that in some cases, we know exactly the hyperkaehler structure that we get on the coadjoint orbits. The example that I showed before with a restricted Grassmannian is exactly an example of this, where the coadjoint, you start with a coadjoint orbit of a compact Lie group, let's say, or of a Lie group of compact type in the infinite dimensional setting, which was our restricted Grassmannian. And then you can have more explicit expression of the symplectic form on the quotient. You can also have the symplectic form as curvature of a prequantum line bundle over these quotient spaces. And this is because, in this case, the orbits are emission symmetric, so very special. For emission symmetric orbits, we know explicitly what we get. And this is one of the papers that I was quoting in the beginning. I mean, it started with this paper, and I have a generalization. So Bigard-Gauduchon got explicit expression of Kähler potential for each of the complex structures. And what I did here is the same kind of ideas, but in the infinite dimensional setting. Hyperkaehler infinite dimensional quotient. I think I will stop here, and thank you for your attention.